Question number 10. A student uses the setup shown to study uniform circular motion. A rubber bug is swung in a horizontal circle of radius 0.5 meter at the rate of 1 revolution per second. The mass of the rubber bug is 30 grams and the string makes an angle of 60 degrees with the vertical. Part A. Draw a force diagram to show all the forces acting on the rubber bug. There are two forces acting on the rubber bug. The first one is the tension in the string, and the second one is its own weight, mg. Part B. Find the angular speed omega and the linear speed v of the rubber bug. Angular speed omega equal to angular displacement per unit time, which is theta over t. From the information given, we have in 1 second the rubber bug rotates 1 revolution, which is equal to 2 pi radian. Therefore, the angular speed is equal to 2 pi radian per second. Linear speed v equal to angular speed omega times the radius, which is equal to 2 pi times radius is equal to 0.5 meter. Therefore, linear speed is pi meter per second. Part C. Find the tension in the string T. Consider the vertical force acting on the rubber bug. We have the vertical component upward is T cosine 60 degrees, which balance the weight of the bug. Therefore, we have T cosine 60 degrees equal to mg. T times 1/2 equal to mg. M is equal to 0.03 times 9.81 g. Therefore, we have the tension in the string equal to 0.589 Newton. Part D. By considering Part C, explain why the string can never be horizontal during the motion of the rubber bug. If the string is horizontal, the tension will be in a horizontal direction, which is perpendicular to the vertical line. In this case, there will be T cosine 90 degree upward force due to the tension, which is equal to 0. As there is no upward force to balance the weight, therefore, the string can never be horizontal. Simon of mass 50 kg is sitting on a merry-go-round 氹氹轉 at 2 meters from the center. The merry-go-round is rotating at an angular speed of 20 revolutions per minute. Find Part A, the centripetal acceleration AC of Simon. Let's have a top view of the merry-go-round. Let O be the center of the merry-go-round. It's rotating at an angular speed omega in a clockwise direction, and the radius is R. And consider Simon is sitting at the position P By definition, centripetal acceleration equal to omega square r, which is equal to 2 pi times 20 over 60 square times 2 equal to 8.77 meter per second square. Part B. Find the centripetal force of Simon and state the origin of this force. Centripetal force on Simon, Fc, equal to mass times centripetal acceleration, which is equal to 50 times 8.77. The centripetal force acting on Simon is 439 Newton. And this centripetal force is provided by the friction acting on Simon. Therefore, the origin of this force is friction. Question number 12. The centripetal acceleration on a body performing circular motion can be found either by using the first equation, A equal to v squared over r, or the second equation, A equal to omega squared r. Peter says from 1, A decreases when r increases. And Simon says from 2, A increases when r increases. If the body now increases its radius, but keeping its period constant, explain which of the above formula, 1 or 2, correctly describe the relation between A and R. By definition, the period of circular motion equal to 2 pi over omega. If the period is constant, then the angular speed omega must be also constant. By the second equation, we have A equal to omega square r. Since omega is constant, therefore the acceleration is proportional to the radius. Therefore, when the radius increases, the centripetal acceleration must also increases. Therefore, the second equation, A equal to omega square r, correctly describes the relation between A and R.